still louder.
ये बंद कर दीजिए अभी दूसरा फाइल
It will not be necessary future. You can close.
This one we are closing.
Close, all close. And first about generalized inverses. Second one. It is first topic.
Control N.
How long should be? Still 1 hour. Still. And another one, still 1 hour.
लाइव चेक करना इसको इंटरेक्ट कर दें ओके कुछ स्टार्ट हो गया रिकॉर्डिंग ठीक ओके
Thank you. We spoke about 3 parts in our GIAN course. First part is a generalized matrix inversion. Second part is about nonlinear optimization. And the third part is about gradient neural networks and zeroing neural networks. Today I will present a short introduction to matrix inversion and generalized matrix inversion, and after that short introduction to nonlinear optimization. From tomorrow we will start with dynamical systems and recurrent neural networks. What we will present in first part aimed to generalized matrix inversion. Particularly, we will introduce the Moore-Penrose inverse, weighted Moore-Penrose inverse, tracing and group inverse. Then we will present some classes of non-unique generalized inverses, so-called IJK inverses, most popular inner inverses, outer inverses with prescribed rank and prescribed range and null space. Also, we will present some minimization properties of generalized inverses, such as least square solutions and best approximate solution. Such minimization properties of generalized inverses will be connection between G inverses theory and optimization. Our GIAN course is advanced. It is aimed to master students, PhD students, professors. But I will shortly present some basic notations, and later my colleague Professor Safika will present more details about this introduction. Here I will present very short introduction to matrix theory, and then we'll start with the generalized inverses. I suppose you are familiar with all notions and notations which I will present here, but I will repeat shortly for your introduction. You know that matrix is written in this form 1. matrix representation assumes that the matrix is divided in rows and columns. Intersections of rows and columns define individual elements. Also, you know that first index represents the number of row, second index represents numbers of column. So if we have element A, ij, we know that this element belongs to row I and to column j. We will use standard notation for n times n matrices over a field F. N is number of rows, n is number of columns. Mainly we will consider fields or given by complex numbers or real numbers. Complex numbers will be denoted by usual notation C, real by usual notation R. Matrix obtained omitting some rows and columns from initial matrix A is called submatrix of given matrix A. If we take determinant of this square submatrix of order K, we will obtain minor of this matrix. Minor of order K is denoted typically as MK. Also, there is very important notation of matrix rank. Matrix rank is a function with the domain given by m times n matrices over a field F, and codomain given by set of natural numbers. And the matrix rank is defined by the following properties, 1 and 2. Property 1 says that rank of zero matrix is 0. Rank of arbitrary matrix A is equal to R if there exists a minor of order R which is different from 0, and all minors or bigger orders are equal to 0. It means that matrix rank is equal to order of biggest non-singular minor. Each minor of order equal to rank of matrix is called base minor of that matrix. Rows and columns which form basic minor are called basic rows and basic columns. Another rows and columns are called non-basic rows and columns. And non-basic rows or columns can be represented as a linear combination of basic rows or basic columns. Matrix rank is equal to maximal number of linearly independent rows or columns. If square matrix is non-singular or invertible or regular, then its columns are linearly independent. It means that there are not rows or columns which can be represented as a linear combination of other rows. So if input matrix is n times n matrix, this matrix is invertible if all n rows or n columns are linearly independent. Also, it means that determinant of non-singular matrix is non-zero. If matrix is non-singular, then such matrix has a unique inverse matrix, denoted in standard way a power -1, and satisfying two classical famous matrix equations. Also, we know that such matrix inverse satisfies many properties. Here are mentioned four main properties, which means that inverse of matrix inverse leads to initial matrix. Here is a relation between matrix transpose and matrix inverse, relation between conjugate transpose, A star, and matrix inverse. And here is reverse order law, well-known property for usual matrix inverse, but not satisfying for both Penrose inverse and another kinds of G inverses frequently investigated in literature. Matrix inverse has numerous applications. Main application of usual matrix inverse is in solving linear equations and linear matrix equations. If we can compute usual matrix inverse, then we can easily solve system of linear equations using this inverse. Also, we can solve linear matrix equation. It is a main application of usual matrix inverse. But with this application, we have connected a lot of other applications. We cannot imagine modern linear algebra without linear systems and without matrix equations. Many mathematical models are represented as matrix equations or as systems of linear equations. Important application is in computer graphics, because many transformations such as rotation, scaling, translating objects are represented in matrix form, and then inverse of such transformation matrix can be used to reverse the transformation. Then there are applications in control theory. Matrix inverse is useful in designing controllers that stabilize and control dynamical systems in control theory. There is interesting to mention that some kinds of 2-3 inverses are applicable in control theory. We will present this later. Applications in statistics, covariance useful in calculating Mahalan of this distance, which is measure of distance between points and distribution. Image encryption and decryption. We want to send one picture in the internet, and then we want to, this contents of this picture don't be visible. We can do this using matrix inverse. Picture is represented in matrix form, then we can use matrix inverse to encrypt this picture, and later receiver can use matrix index again to obtain original picture, because inverse of inverse matrix is original matrix. Applications in nonlinear optimization, we will speak about this more in third lecture. Inverse of Hessian matrix defines well-known Newton method for nonlinear optimization. Hessian matrix is matrix of second-order partial derivatives. Then application in solving normal equations. How to describe normal equation? We want to solve a linear system AX equal B. This system can be consistent and can be inconsistent. If this system is inconsistent, we have no solution. Then we must find some approximate solution, such as least square solutions or the best approximate solution. One way to obtain this is to multiply this inconsistent linear system and obtain such normal linear system in form of normal equation. A transpose is used for this multiplication, and in case if A transpose A is full rank matrix, then we can use matrix inverse, usual matrix inverse, and obtain solution of this system. What is important here, AX might equal B is not always consistent, but normal equation A transpose AX equals A transpose B, yes. Finally, this expression, inverse of A transpose A times A transpose is Murphy-Ross inverse of A. What if matrix is rectangular? And what if matrix is not invertible? Then we cannot stop linear algebra. We still must solve some important systems of linear equations, and still want to solve many linear matrix equations. Then we need to extend the notion of matrix inverse to notion of generalized inverses. Usual inverse is unique, but opposite to this property, generalized inverses are not unique. There are many classes of generalized inverses, and I will mention here three properties which are desirable in defining generalized inverses. First property is that G inverse, shortly, generalized inverse or G inverse, exists even for rectangular and singular matrices. Generalized inverses should inherit as much as possible properties of ordinary inverse. And such defined G inverse should inherit some properties of ordinary inverse. If these three properties are not satisfied, then we cannot say our G inverse is properly defined. Last years, many different kinds of G inverses are defined. Mainly, researchers consider composite, I call it composite generalized inverses. Such inverses are defined as a combination of well-known G inverses. Main G inverse considered is so-called Moore-Penrose inverse. Most simple and most frequent way to introduce Moore-Penrose inverse is based on usage of these four matrix equations. These matrix equations are denoted by 1, 2, 3, and 4. Star in exponent means conjugate transpose matrix. There is only one matrix which satisfies all four equations, 1 to 4. And this G inverse is known as Moore-Penrose inverse. First who discovered such inverse was Moore in 1920. But this result stayed unknown 35 years, and in 1955, Penrose discovered a very useful application of Moore-Penrose inverse in solving linear matrix equations and solving systems of linear equations. And because of that, Moore-Penrose inverse is used with this name. It is confirmation that applications of G inverses is very important. Possible that reviewers and editors of scientific journal will ask about some applications. Another unique G inverse is Drazen inverse. It is unique solution of matrix equation 2 and two additional matrix equations, 1K and 5. Property 5 means that Drazen inverse is commutative with original matrix. In property 1K, we have one integer, one natural integer, which denotes index of matrix. We know that if we multiply matrix and make powers of matrix, rank of matrix cannot increase. Typically, matrix rank with powering increases, and in one moment, we will obtain rank invariant powers. This point where rank invariant powers are obtained is called the index of matrix. If we consider solutions of only matrix equation 1, such G inverses are called one inverses or inner inverses. One individual inner inverse is denoted in this way. If we consider only equation 2, we will consider class of two inverses, one individual, two inverse or outer inverse is denoted in this way. Then popular G inverses are reflexive G inverses, which satisfy equations 1 and 2. There is unique Moore-Penrose inverse, unique group inverse, which satisfies equations 1, 2, and 5. Drazen inverse, and so on. We can consider different combinations of G inverses. Outer inverse, class of outer inverses is class of matrices, which satisfy only equation 2. Set of outer inverses with prescribed rank S is denoted in this way. S in index means that it defines rank of involved outer inverses. Also, there is notion of image range and null space. It is interesting to consider outer inverses with prescribed range and prescribed null space. We know that such inverses with outer inverses with prescribed both range and null space are unique. And typically, many of composite G inverses defined in literature are outer inverses with prescribed range and null space. Moore-Penrose inverse is one particular outer inverse with prescribed range and null space equal to range and null space of conjugate transpose. Weighted Moore-Penrose inverse is outer inverse with range and null space. Drazen inverse is outer inverse with range and null space related with index of matrix. Group inverse is Drazen inverse in particular case when index is equal to 1. And lemma 1 gives one useful property of reflexive inner inverses. This property is related with class of inner inverses, outer inverses, and matrix rank. Evidently, rank of outer inverse is less than or equal to rank of A, because such inverse satisfies matrix equation 2, and rank of outer inverse cannot be bigger than rank of A. Opposite, rank of inner inverses is greater than or equal to rank of A. And if we have a property that rank of X is equal to rank of A, then such inverse will satisfy both, must satisfy both of matrix equations 1 and 2. What is useful to learn from here? If we have a result from outer inverses, we can obtain immediately result from reflexive inner inverses if we consider rank equal to rank of A. Here are in lemma 2 the main properties of Moore-Penrose inverse. If we consider the non-singular case, invertible case, evidently all of these properties will be satisfied. Here is usual definition of eigenvalue and eigenvector. Eigenvalues and eigenvectors are defined by these equations. About this, Professor Pick will say much more. So here is only short introduction because we need in our representations of the inverses definition of eigenvalues, definitions of eigenvectors. Here first and very important usage of eigenvalues. If we consider eigenvalues of matrix A star A, then we will obtain singular values of matrix. And after that, we can compute so-called singular value decomposition of matrix A. Very important decomposition. appropriate for computing Moore-Penrose inverse according to singular value decomposition, as we did shortly. Arbitrary matrix can be represented as product of two unitary matrices, A, U, and V, and one particular one. So, appropriate matrix made of diagonal matrix and 3 zero blocks. One block is made of singular values on main diagonal, and another block, 3 blocks are zero blocks. In shortened, more compact form, it is presented in this way. Of course, sigma, capital sigma, means diagonal matrix with singular values on main diagonals. Then Moore-Penrose inverse can be easily computed using such a representation. Here is made unitary matrix V. In right hand side is unitary matrix U star. 3 zero blocks stay. And here is diagonal matrix with reciprocal values of singular values. This diagonal matrix will be presented in sigma -1. Very important and most frequently used representation for computing Moore-Penrose inverse. And there are similar representations for another kinds of G inverses. What is drawback of this approach? Drawback is diagonal matrix 1 by sigma 1, 1 by sigma r. What is the drawback here? If singular values are too small, then we will have division by 0, almost division by 0. But find something better than singular value decomposition is impossible. I think singular value decomposition is main approach in computing limits. Many programming languages include standard functions for computing Moore-Penrose inverse, and singular value decomposition is inside this implementation. MATLAB has a standard function PIB for computing Moore-Penrose inverse. If you have such problem, division called division by 0, in case when singular value is too small, it is better to avoid this part and put 0. It is better to put 0 here. You will obtain approximation of Moore-Penrose inverse, but better is to obtain approximation than nothing. Important is to mention that if we have singular value decomposition and Moore-Penrose inverse, we can generate complete class of inner inverses. It is enough to replace 3 zero blocks by arbitrary matrix S1, S2, and S3 of appropriate dimensions. An important topic in computation G inverses is based on matrix decompositions. There is a big number of different matrix decompositions. I will mention here several matrix decompositions. More decompositions are available. Later, Professor Safik will speak more about available decompositions. For our research here, most important is to mention so-called full rank decomposition. We have m times n matrix of rank R, and then it is possible to find two matrices P and Q such that A is represented as product of such two matrices. Matrix P is of full column rank. Matrix Q is of full row rank. And then we can represent Burg-Penrose inverse easily in such form, which is given by product of right inverse of Q and left inverse of P. In this way, we reduce problem of computing Burg-Penrose inverse on problem of computing usual matrix inverse. First term is given here, and it represents right inverse of Q. Second term is represented here, and this term represents left inverse of P. There are another matrix decompositions such as LU matrix decomposition. Again, more about LU decomposition will be presented later. L is lower triangular with ones on main diagonal. Lii is equal to 1. And U is upper triangular matrix. If we have LU decomposition of matrix A, then we can solve system AX equal to V using two simple linear systems. Two systems, but much more simpler. Even we have explicit formulas how to compute, how to solve such linear systems. If U is equal to L transpose, then we have Cholesky decomposition. And here I presented formulas how to obtain explicitly solution of linear system. Sometimes we cannot obtain LU decomposition directly. We will need permutation matrices. It means that during Gauss elimination, we will need to exchange some rows on columns. Then here will be some permutation matrices. And then we will present one important, let's say, most important application of generalized inverses. It is application of inner inverse, one inverse. And now we started serious topic, serious investigation of G inverses. We want to solve linear matrix equation AXB equals D. A, B, D are given matrices, and of course they must be of appropriate order. X is matrix which we want to compute, unknown matrix. Problem is how to find matrix X. If A and B are invertible, it is easy job. If A and B are invertible, multiply left by inverse of A, right from inverse of B. But if it is A and B are not invertible, then problem is solved using one inverse. Main result says that such linear matrix equation ax b equals d is solvable if and only if such condition is satisfied for arbitrary inner inverses of A and B. Which inner inverse is most appropriate? Either. Of course, Moore-Penrose inverse is most appropriate here. We can use here Moore-Penrose inverse as a representative of arbitrary one inverse. And in this case, the general solution is given in this form. Here, Y is arbitrary matrix of appropriate dimensions. So here is, I will say, most important application of G inverses. Using inner inverses, we can continue linear algebra. We can solve such a linear matrix equation. If we multiply x, this x, by A from left and B from right, what we will obtain? Here we will obtain A1D, B1B plus A YB minus A1A, but it is A. A1A is A, Y, B, B1B, again B, and it will be cancelled. And we will obtain only A1D, B1, B, and it is D. What if this condition is not satisfied? A1D, B1B. If this condition is satisfied, we have no solution. Definitely. See, linear matrix is not solvable. Sometimes researchers will say inconsistent, and definitely we have no solution. What is exit from this point? Exit is to find least fair solutions, find best possible solutions, find least fair solutions, and find best approximate solution. It is not exact solution, but finds something which approximate this matrix equation. Such solutions will not give exact solution. Ax b will be exactly equal to d, but will be approximately equal to d. Here is lemma 6, which is important in the sense that this lemma says we can compute inner inverse easily, and inner inverse always exists. Here is one representation of matrix A obtained after Gauss-Jordan elimination, permutation matrices, and here is row reduced echelon form, kind of reduced echelon form. I is identity matrix of order R, matrix of K of appropriate order obtained after Gauss-Jordan elimination. And then X can be represented simply in this way, where L is arbitrary block. Of course, inner inverses are not unique. And here is one arbitrary block which describes different inner inverses. If we want to solve system of linear equations, we can consider this as a particular case of linear matrix equation AX B equals D. Then such system is consistent, or such system has solution if this condition is satisfied, A1 B equals B, for arbitrary inner inverse. Best choice is, of course, Mulpenrose inverse. And then here is general representation of solution to system 5. Interesting is to mention that arbitrary one inverse will give the same solution. We can change here inner inverses, but solution will be AX will be again equal B. We can try. AX is equal to A1B plus what will be if we multiply this by A from left. What will we have here? A minus A1A, which is 0. And we will obtain here A1B, which is equal to B. But A1B equals B is the same as say B is in range of A. It requires some knowledge of functional analysis and so on, but functional analysis is how to say, correlation with the numerical linear algebra. Do we have some talk? So, A1 equals B, we can go in B. B is range image of A. Then AX equal B is consistent. Of course, we want to solve AX equal B. Of course, the condition B in range of A is, how to say, natural requirement. Here is part from range of A, left part, the left hand side is in range of A, and we must require that right hand part is also in range of A. If not, if B is not in range of A, then again we will have no solution, but we can find least square solution. There are definitions of matrix norms, and first definition 2 gives main properties of matrix norm. About matrix norm, Professor Static will say more. Here is only short introduction that you know what is matrix norm, and later you will learn more. There are 4 properties of matrix norm. First property is non-negativity, which means that matrix norm is non-negative function. Matrix norm is 0 only for 0 matrix. Property about matrix norm and scalar value lambda. Triangle inequality. And each matrix norm must satisfy such 4 properties. There are several definitions of matrix norms. One norm or maximum column sum norm, induced 2 norm, spectral norm, maximal eigenvalue. sigma maximal eigenvalue. Infinity norm or maximum row sum norm. Frobenius norm. Defined using matrix trace. Matrix trace is sum of diagonal elements of main diagonal. For our future research, for applications in recurrent neural networks, Frobenius norm will be most useful. Why Frobenius norm is most useful? Because Frobenius norm is defined using matrix trace, and there are possibilities to take derivative with respect to matrix norm. We know that derivatives are important in nonlinear optimization, and Frobenius norm is most important in defining recurrent neural networks. I had many questions during my presentations. Why not use another matrix norm? Of course, why not another matrix norm? But we need rules how to compute derivatives with respect to another matrix norm. Then we can define gradient with respect to another matrix norms. If we have such possibilities, of course, we can use another matrix norm. There is definition of Frobenius matrix norm. Here is matrix trace, defined as sum of elements of main diagonal, or matrix trace is equal to sum of eigenvalues of matrix. There are some important properties of matrix trace. About matrix trace you will see later more. Important property is that trace is not commutative but invariant under cyclic permutations. In this way, we will obtain such property, trace of A, B, and B, A are equal, but it is not according to commutativity. It is according to this cyclic permutations property. No. Here is this situation when we want to solve system of linear equations AX equal B, but B is not in range of A. Condition A1, B is not satisfied, and we have no solution. We will say that such system is inconsistent. There is practical tool in linear algebra how to find if system is consistent or no. Well-known Kronecker-Capelli statement, frequently investigated in many faculty courses. We can consider augmented matrix, matrix with original, block matrix with original matrix, and with right-hand side. If matrix A and the block matrix AB are of the same rank, then such system is solvable. And there is unique solution if rank of A is n, is equal to n, number of Colemans, number of unknowns, or number of Colemans. And we have infinitely many solutions if rank of A is less than n. N is number of Colemans or number of variables. Of course, if number of linearly independent rows in A is smaller than number of variables, we cannot solve system. We have less linearly independent equations than number of variables. And of course, subsystem is not solvable. There is possibility to find least square solution. Least square solutions satisfy this condition, norm of arbitrary least square solution must satisfy AU minus B, norm is less than or equal to norm of AX minus B. Important property is given in proposition 3, and this property says that 1, 3 inverses satisfying equation 1 and equation 3 are related with least squares solutions. So solution XB is a least square solution if and only if X is 1, 3 inverse. First part says that norm AX minus B is smallest when X is given as product of 1, 3 inverse and B. And opposite, if we have a least square solution, that this least square solution must be defined using the 1, 3 inverse. And there is another property of minimum norm, of minimal norm. If we want both of these, minimum norm property is related with 1, 4 inverses. If we have a solution of minimum norm, this solution is related with 1, 4 inverses. And if we ask a solution defined by 1, 4 inverse, then we will obtain minimum norm solution. And if we unify both least square solution and minimum norm solution, then we will obtain Moore-Penrose inverse solution, or best approximate solution. Best approximate solution is a least square solution of minimum norm, minimal norm. Do we need minimum norm property? Least square solution is enough. Many researchers in control theory investigate situations when another least square solution gives even better solution than Moore-Penrose. Of course, it is possible to find some 1, 3 inverse sometimes, which gives smaller residual norm of AX minus B. But Moore-Penrose inverse is unique. 1, 3 inverses are not unique, so that it is always good to use Moore-Penrose inverse. Finally, many programming languages possess standard functions for computing Moore-Penrose inverse. Here is general solution. A dagger, Moore-Penrose, B plus nilpotent part. If we multiply left from left by A, we will obtain 0. This part is from kernel of A. One Moore-Penrose solution plus one expression from kernel from null space of A. And of course, then norm of Moore-Penrose solution is less than or equal to this norm. Some applications of generalized inverses. Yes, many reviewers will ask you for applications. Many editors will ask. Many journals will say not appropriate for our journal because we need applications. Many IEEE journals will not accept your paper, will reject immediately if you have no application. There are some possibilities to find some applications, and then your paper will be better, much bigger probability to be accepted. First application, most important, I will say again, is application is solving system of linear equations in matrix equations. If we consider original AX equal B, then Moore-Penrose inverse is there. But if we consider constrained system AX equal B with some constraints, for example, constraint of the form X in range of A or something, then it is possible again that another kinds of G inverses are applicable directly. Of course, this application is again based on Moore-Penrose inverse. I published several such papers, and reviewers always ask, is it better than use Moore-Penrose inverse? No, it is not better. And probably it is better on application of Moore-Penrose inverse. But some particular inverses are directly applicable. Applications in linear regression, in statistics, signal processing, control systems, image processing. Here I put a reference to one book, which was my first book in image restoration. I investigated this topic. There is possibility to present matrix, gray matrix, in matrix form, with pixels given with values from 0 to 255. Color image is represented as tensor. And then 3 times something. And if we have representation of matrix of picture in matrix form, then we can represent some matrix damages, picture damages in matrix form also. There is exact rule how to represent uniform motion. For blue, uniform motion is represented in one matrix equation. And then we can obtain original matrix. We have equation of the form AX equal B. Original. It is original picture. And now we want to find. Here is matrix damage. Here is visible matrix. Current situation, but this B is destroyed. And then we have linear matrix equation. It can be considered in tensor form. It will be useful to consider in tensor form. Then Moore-Penrose can be applied here. Finally, here we will have some structured matrices. For linear uniform blue, it will be Teplitz matrix with main diagonal parallels. Applications in statistics, economy, and game theory. Machine learning, Moore-Penrose inverse, nonlinear optimization are the basis of machine learning. how to compute generalized inverses. Two possibilities, classical numerical algorithms and continuous time neural networks algorithm. Here we will consider part 2. Part 1 is enough for another course. For another time. After several years or next course, it will be appropriate to consider classical numerical algorithms. Classical numerical algorithms can be direct and iterative. Direct methods typically compute solution in finite sequence of operations. We exactly know computation is finished, we will obtain G inverses. Iterative methods start from appropriate initial solution and improve this solution, improve during iterations and never continue. We will stop with solution obtained with desired accuracy. Main direct methods are methods based on singular value decomposition, method based on another matrix decompositions, such as full rank decomposition, QR, value decomposition, method based on application of Gauss-Jordan elimination, Greville partitioning method with the RFADEV algorithm. SVD is main and typically used. Iterative methods, Newton iterative method, high order, hyperpower iterative methods, methods of arbitrary order, method based on optimization. Of course, we can always minimize Frobenius norm. Sway, typical sway, because we have sway routine definition of Frobenius norm and one how to prevent number 2. Here is a limited representation of generalized inverses. Well-known limited representation of Moore-Penrose inverse plus lambda A term is related with Tikhonov regularization. Important properties. Moore-Penrose inverse is related with A star, conjugate transpose. Drazen inverse is related with powers, rank invariant powers. A power k, where k is index of A. And then, if we replace A star and A power k with arbitrary matrix, we will obtain outer inverse. It is useful, very useful and practical tool how to generalize and obtain more general results. When you have result about Drazen inverse, when you have result about Moore-Penrose inverse, you can easily obtain result related for arbitrary outer inverse with prescribed regional space. It was useful tool. I used this tool many times in my research. When I found result about Moore-Penrose, immediately I have a result how to obtain outer inverse. Okay. Here is tutorial. Approximately, which was 1 hour. It is for this tutorial. Introduction to generalized inverse. This stuff we will continue later. Probably now it's time to ask questions.
Yeah.
Something.
Yeah, if you have question, please.
So we mostly use Frobenius norms.
Frobenius norms.
Can you give mic?
I spoke about this, about why we use Frobenius norm, because Frobenius norm is related with trace or matrix And there are some now formulas about how to compute derivatives of Frobenius of matrix space. We can use another norms, but we should devise, should find related how to compute derivatives with respect to another. And it will be very result.
And in the Tikhonov regularization, the lambda value we choose.
Lambda,
Hmm.
regularization parameter. I tried numerical experiments with lambda.
So
Mainly, I use lambda equal 10 power minus 1. Results are typical notebooks. You take something, results typically are notebooks. But we can reduce lambda equal to 10 power minus 4 gives the result. Then I tried many times to use even smaller values, 10 power minus 6, power minus 8, not
and what is the main difference between Drazen inverse and generalized Moore-Penrose inverse mainly?
And the reason inverse is applicable only for experiment. Moore-Penrose inverse is applicable, and you need many times, to arbitrary matrix. Then, Moore-Penrose inverse is related with singular value decomposition. Related with conjugate transpose matrix. The Drazen inverse is related with rank invariant powers. Drazen inverse can be expressed using the Jordan decomposition. Jordan decomposition, Corneal, it is kind of Corneal-Potent decomposition, surely on the association of the gene versus you different forms of Corneal-Potent decomposition.
So what are the main differences between Drazen, generalized Drazen and weighted Drazen inverses?
Generalized Drazen inverse.
Yes, sir. So Drazen inverses, generalized Drazen inverses and weighted Drazen inverses.
Here we will not investigate generalized Drazen inverse. We will consider Drazen and Moore-Penrose inverse.
What is the difference between Moore-Penrose inverses and weighted Moore-Penrose inverses?
Weighted Moore-Penrose inverse. Because weighted Moore-Penrose inverse is related with this matrix, related with two positive definite matrices N and L. And the range and null space of weighted Moore-Penrose inverse are defined using this matrix. Consider with range and null space with this matrix.
In the special case of quartet, if M and N are identity matrix, it will be considered with the Moore-Penrose.
Then equations which define Moore-Penrose, weighted Moore-Penrose inverse will be different. There are these definitions. Here will not be AX star equals A, will be MAX, and here will be XAN minus 1 star equals XAN minus 1.
So, weighted, you can think of this generalized kind of more general. So when you specify as identity matrix, it will coincide with the usual Moore-Penrose inverse. So that way, it can.
Then we should we apply weighted case only or genus not only weighted multiple, basically, when we cannot multiply, when matrices are not of appropriate dimensions, then we can put weights, one or two weights, and solve this problem. For example, if tracing index is defined only for straight matrices, and if we want to extend definition to rectangular matrices, we will use weighted tracing index. It is named Golan problem.
What is the need of introducing weight in multiple resilience?
Weighted, not random. I
What is
call
the need of introducing weight?
weighted multiples. There is a reason to introduce weighted tracing index, I thought. Because tracing index is applicable only to square matrix case. And weighted is applicable to another, to all cases. Here we have our, if we want a rectangular case, we must insert one weighted matrix W to make possible multiplication here. And weighted multiples. Why do we go weighted multiples? Okay.
Your question?
When we have incompatible matrices not appropriate for multiplication, then we can insert appropriate weight.
Now, repeat that one.
Professor Sergut, all the results for weighted multiples will be more general. It was algorithm how to introduce another weighted generalized index. Okay. No questions?
Sir, how these different types of new generalized inverses are found? So how these new types of generalized inverses are found? So as you see, we have more Penrose inverses and Rajin inverses. Then how DMP inverses is found?
How
Rajin
DMP?
Yes, sir.
DMP, not only DMP, many kinds of gene inverses are introduced.
Yes, sir.
Finally, I must say that such investigation about composite inverses are dominant. This research is now dominant. Okay, we can speak about this BMP. Is it true? Then there was composite gene inverse based on group inverse here. What is that?
First, how these inverses are found? How one can think that he will introduce a new type of generalized inverse. What is the need to introduce a new type of generalized
And
inverse?
there are a lot of cases. On right hand side, left hand side, dual case. And in my research, I presented outer NP inverses, how to say. Here, I wanted to put here outer inverse. And I think it will be the end in this research for composite. In this. In general, in the beginning of my research, I was not interested in theory of such inverses. Because GMP inverse is one outer inverse. It is one outer inverse with prescribed range-north phase, and I can apply all noun representations about outer inverses, the inverses with prescribed range-north phase. And I wanted to put here outer inverse and say it is end, it is state of art in this research, published subpaper. I can prepare for you if you are interested. Here it is possible to put arbitrary outer inverse with prescribed range-north phase. But people started still to investigate it. After all, I want to prepare one final paper about this. And such combinations with Murpenrose, Dracing inverse, without an inverse, which is now dominant research in genetics. We can see later one GNN representation of this inverse.
So where is the host? Which managing the system
Will we continue immediately
or
or
after lunch or?
yes? It started later. Sign for lunch.
Recording stop. So, after lunch.
About the MP in the speaker.
So now we have lunch or?
You finished the lecture?
One lecture finished.
So after lunch we will do. Okay, lunch. Lunch.
And then plus time. Next class time.
देख लो टाइम टेबल में हमारा एडजस्ट हो रहा है जो 2 से 3 चला
And so that's very short.
the
2 p.m.
2 4
2 p.m. and we always.
other 2:30 कर दो 2:30 नहीं ये नेक्स्ट
Lecture. इसको आप कोर्स में ट्राई करिए
सर ऑडियो आया कि नहीं? नहीं नहीं, इसमें अपन ये इसको प्ले तो करें। अरे बैक्स में तो ऑडियो आ ही जाएगा ना। अभी अपन तू क्या बोला, माइक्रोफोन डिफरेंस सेलेक्ट करें क्या? मैजिक कहाँ है? नहीं अभी देख तो अपना ये आ गया, तो लाइन में ऑडियो आ गया, अपन इस तरीके से किया था। ठीक है। हेलो हेलो। हाँ ये कैप्चर को इनेबल क्या कर दिया। अभी है ना, मैं इसको डिसेबल कर रहा हूँ। यहाँ से स्ट्रीमिंग करना स्टार्ट करना पड़ेगा।
बोल देना जहाँ से ये हो
हाँ सर, मैं
उसको
उसका नेट बंद हो गया था सर बीच में, तो इसलिए सर
कॉम्प्रोमाइज नहीं करना है। नेट क्यों बंद हो गया?
नेट कुछ सर इशू आया था, तो इसलिए सर दोबारा से जो है
थोड़ा एक्स्ट्रा
रिकॉर्डिंग तो हो रहा है, तो दिक्कत नहीं।
हो रहा है ना।
जैसे कि मीटर चेक करना, उस पर आया था हाँ? जो मैंने ग्रुप में शेयर किया, लिंक व्यू आ गया रूम का, ठीक है। Just change your side. Can you change your side? Yes.
Can
Yes. Change it or
Yeah.
Yeah.
works. Okay. First criterion is small gradient norm. Another is small norm of difference between two iterative points. Third criterion is small change in loss function, in goal function, in objective function. Another criterion is maximum number of iterations. When do we use this criterion? When convergence is very slow and gradient descent goes slowly to minimum, and we must wait days and days to obtain minimum. Then we can stop iterations after predicted maximal number of iterations. Another important criterion, stopping criterion, is early stopping. When do we use this stopping criterion? You obtained, for example, accuracy of 10 power minus 5, for example, which is not so good precision, 10 power minus 5. And you want better, want to continue with iterative points, but because of numerical instability, because of accumulation around of errors, you will obtain divergence. And after several iterative steps, you will obtain rapid divergence. Because of that, it is better to stop future iterative steps. Best choice is to make combination of these different stopping criteria. Combine B and C is frequent, D is always here. And in many numerical experiments, we will find strike in tables. Strike will say that minimum is not achieved after predefined number of iterative steps. What are advantages and disadvantages of gradient descent methods, better to say, because this method is not unique. Advantage, GD, gradient descent methods are globally convergent to local minimum, regardless of the starting point, desirable property. Because of property 1, many optimization methods switch to GD when they have problems in convergence. Many better optimization methods, typically more complicated, when have problems with numerics, with instability, switch several iterations to gradient descent method to stabilize convergence and then continue in normal way. Newton method uses this technique. When Newton method starts to diverge, to increase goal function, then it is good to switch several iterations to gradient descent method. Disadvantage, convergence is linear and usually very slow. This method can lead to orthogonal successive directions. Here, this phenomenon is called zigzagging. Here is one example. Zigzagging. We always trace minus gradient strictly, go zigzag to orthogonally to level lines. Newton method for nonlinear optimization is next method which we'll explain. Newton method for nonlinear optimization is obtained using second order Taylor development of goal function. Goal function with respect to D, to direction. Second order Taylor expansion for multivariate function is defined in this way. Then we use partial derivatives with respect to both terms, another, using results from numerical linear algebra, and obtain that partial derivative of goal function with respect to D is 0 if and only if this condition is satisfied, and which means that direction D, this direction is given as minus inverse of Hessian times gradient. In gradient descent, we have only minus gradient. Here is matrix GK made of second order partial derivatives, and finally inverse of this matrix. And pure Newton method is defined in this way. Pure Newton method is fastest, second order of convergence, because it is based on second order Taylor expansion. Theoretically looks excellent, but practically not at all. What is disadvantage, the main disadvantage of Newton method?
Inversion of the Hessian.
Yes, in inverse matrix of Hessian. First problem is to make Hessian second order partial derivatives and make matrix of second order partial derivatives, and finally compute inverse of this matrix. It is problem which can be even harder than initial points. Advantage is very fast.
So one step.
If start convergence can finish quickly. Fast and wide method. If we start far from minimum, then it is difficult to obtain convergence. If we start near minimum, convergence will be fast. For quadratic functions, we will obtain convergence very quickly. It is important to mention that compute decent direction as product gk minus 1 times gk small gk is difficult. Much more efficient method is to solve this linear equation with respect to d and obtain decay in this way. Here are iterations of method known as Newton method with line search. What is difference between Newton method and Newton method with line search? Differences in step size, decay included in a pure Newton method definitely works or weakly or will not work. Step size we can how to say stabilize Newton method and can lead to global convergence, which is okay, but still problem with Hessian and inverse of Hessian remains. Sometimes after numerical experiments, GK can not be positive definite finally. Sometimes GK is almost singular. Best way is to use modifying Newton methods. And we can say that now in nonlinear, in unconstrained nonlinear optimization, quasi-Newton methods are most popular. Instead of using inverse of Hessian, we will use approximation of this inverse. Of course, approximation will not give so good results in one iteration. In future, will give. Finally, it is better to spend much more iterations using simple approximations of inverse of Hessian than a much smaller number of approximations in Newton methods. There is a rule how to define approximations. BK is approximation of Hessian matrix. HK is approximation of inverse of Hessian matrix. And here is a requirement how to define how to approximate inverse of Hessian. SK is difference between two iterative points. YK is difference between two successive values of gradient. If we use approximation for BK, later we must use inverse. If we need approximation of inverse of Hessian, we will use first equation. We will need to solve such vector, such a system, such a linear system. Here are several rules about quasi-Newton updates. Typical requirement is quasi-Newton update should be positive definite because Hessian matrix second order partial derivative is symmetric, positive definite. Another rule in quasi-Newton modifications is to use low order approximations. I mentioned here only 3 quasi-Newton updates. In literature, we can find great number of different quasi-Newton updates. Here is one popular symmetric rank 1 update, SR update, defined in this way. This updating rule, SR1 rule, uses here is vector column, vector row. We have here multiplication of vector column and vector row, and it is matrix of rank 1 because this part and another part are of rank 1, only one column or one row. And if we multiply such two vectors, we will obtain matrix of rank 1. And here is row times column. It is scalar product, it is number. And here all is simple. We have number obtained using the scalar product, and here is vector multiplication. It is much easier than compute second order partial derivatives and compute inverse of this matrix. DFT updates, DFG, Droid and rule is, for example, here present. Now dominant quasi-Newton updates. Every day we can find, almost every day we can find new methods about quasi-Newton updates. Here is general quasi-Newton algorithm. Objective function is input. Initial point again, and again tolerance for stopping criterion. Start from 0, from initial point, and perform while cycle inside, compute decay, search direction as approximation of inverse of Hessian times gradient. Compute step size decay using inexact line search, for example, backtrack or another. Compute new approximation, update iterative steps counter, find new approximation of inverse of Hessian. And when we finish this cycle, we will return output. It was minimum about gradient descent methods, about Newton method with line search, about quasi-Newton methods. Here I want to point you my research interest in this area. What was my main research interest here? We wanted here to put another parameter. If we consider rule of form new iterative point equals old iterative point plus step size, search direction, it will be line search method. We wanted new class of iterative methods with another parameter, with another step size. And first result published in this research was published in Numerical Algorithms, 2010. We call such class of algorithms accelerated gradient descent methods with line search. Accelerated. What is acceleration? Acceleration is new parameter. Problem was how to define TK, another parameter TK. Our idea was to use simplest approximation of inverse of Hessian. Use Hessian as diagonal matrix, only diagonal matrix. Constant diagonal matrix in form inverse of scalar value G, gamma K, and identity matrix. I is identity matrix of our images. Simplest approximation of inverse of Hessian. It is far from inverse of Hessian, but faster in making iterations. We will make much more iterative steps, but much more simpler. And here we obtain new iterative rule of the form 13. Here, theta k, additional parameter, is defined as inverse of this scalar value of this number. How to obtain this new scalar, gamma k? Again, Taylor expansion. Taylor expansion, gradient minus gradient Hessian. It is mathematical tool in nonlinear optimization. It is main mathematical tool. Make second order Taylor expansion. Use this point in middle between two successive approximations in xk plus 1. And obtain a rule how to compute gamma k during iterative steps. Theoretically, it was fine, 18 was fine, but practically during iterations, we sometimes obtain negative values or 0 for gamma k plus 1. Theoretically impossible, but numerically, during some errors, round of errors, it was possible. And we wanted to prevent these situations. And when this value is less than 0, then we will use 1. Go to safe gradient descent method. Obtain negative gamma is dangerous because then we will go to maximum, not to minimum. And in that way, we obtain improved gradient descent method with 2 parameters. 10 minutes more. You'll be soon. I'm only going to present some possibilities what was possible to do in this research. Another idea was to use, instead of one simple TK, use this expression. TK is between 0 and 1. So TK is bigger than TK squared, bigger than TK third, and so on. And evidently we have such 2 inequalities. And if we use this expression, we will increase step size. Increase here is greater than or equal to with respect to TK. But this increasing will not be so far. So if intention was to exploit, obtain step size and direction longer, slightly longer than only one step size. This result has been published in Optimization Methods and Software. Another idea was to use Picard-Ishikawa hybrid iterative process and obtain some improvement of nonlinear optimization method. Put instead of mapping arbitrary mapping T, iterative rule for nonlinear optimization. And when we put it improved gradient descent, we obtain one more parameter, alpha k plus 1. Alpha k is between 0 and 1. But alpha k plus 1 should be greater than or equal to 1. Another possibility for research in this direction was to use fuzzy logic systems and neutral-sophic logic system. Fuzzy logic system is defined on one membership function. In neutral-sophic logic system, we has 3 membership functions: truth, falsity, and independency. When we vote, we can be yes, we can say yes, no, and sometimes I don't know what to say. And idea was to define 3 membership functions: truth, independency, and falsity. All membership functions can be between 0 and 1. So this relation is evident. And our idea was to put one additional so-called fuzzy parameter before step size. What was the rule of this fuzzy parameter? The rule of this parameter was to trace behavior of Boole functions during iterations. If we go slowly to minimum, then increase step size. If in opposite size, decrease step size. And it should be job for fuzzy logic rules. We must have several neutral-sophic rules. If then rules how to define Nikkei, new fuzzy parameter. Nikkei is defined according to behavior of Boole function during iterations. This result has been published in Symmetry recently. And in this way, we can obtain class of iterative methods. We can obtain classification of each of arbitrary nonlinear one additional fuzzy parameter. This additional fuzzy parameter is aimed to trace behavior of error function and increase step size, reduce step size. It is general rule. Nikkei is less than 1 if goal function increased, greater than 1 if it is smaller. If we reduce goal function, then increase step size. If we obtain non-wanted results, then reduce step size. It was not easy to find membership functions. Membership functions must be controlled strongly. If we use big values, we can go to unwanted direction, to unwanted situations. I asked help of several people to help us how to define membership functions. Asked Fedela Panak from Milan for it. Minutes. Then after posification, neutrosification, better to say, not neutrosification, we use the neutrosification rules. Here are the rule how we carefully defined membership functions. Here is situation when goal function decreases during iterations, we use above values. Here is opposite situation. And finally, I will only mention about possibility to use conjugate gradient methods. Conjugate gradient methods use gradient in a current point, but also use information from previous direction. Idea is to trace motion from previous direction and increase convergence in future. Here, all this direction is kind of momentum. How to use the previous information and avoid local minimum. Here are main conjugate gradient parameters. Here is conjugate gradient parameter beta k, which must be selected carefully. And there is big number of conjugate gradient methods according to selection of conjugate gradient parameters. Here is another class of conjugate gradient methods. Idea is to define properly beta for people interested in gradient neural networks. It will be possible to define conjugate gradient neural networks instead of using the gradient method to define neural network. Idea is to use conjugate gradient method. And possible to use gradient neural network with momentum. Questions?
Okay, if you have any questions.
SR method, you use the line search. You use the line search, exact line search or inexact line search?
Inexact.
So in
Exact line search I used in the beginning of my investigation or non-linear optimization. Then it will be necessary to define the new goal function in terms of step size and find minimum of this. Inexact line search is done.
And in exact line search, which conditions do you use? The goal state RV job or only goal state?
It use goal function. One criterion must be satisfied. And the first time when this criterion is satisfied, we will stop.
No, I was asking in exact line search, which conditions do you use? For backtracking.
Depends on inexact line search. Here is one of inexact line search is backtrack line search. This condition we use. Define sigma in this interval. Define beta, for example, 0.8. And then start from 1. Start step size from 1. And verify until this criterion is satisfied, reduce step size by beta. First time when we have opposite inequality, stop. Inexact line search. reduce goal function enough. Don't try to find optimal range. Interesting is to apply continuous gradient methods in defining neural networks. This research is new and there is a finally, in terms of case, will be possible.
So my question is about SM algorithm.
About
That SM algorithm.
SM,
Ah.
SM method. SM method. SM method means Stanimirovich, Miladinovich. We probably use
That-
our surnames to define this method. SM method.
Um,
SM method starts here. Mhm. We wanted to include another parameter.
in that we are using diagonal approximation of the Hessian.
Yes,
So
constant diagonal approximation.
so it
There is variable diagonal approximation and arbitrary
so
positive.
those are too far from the actual approximation for the Hessian.
Too far from exact.
My question-
So this year. But it is one approximation and we expect much more iterations. Seem to.
My question was about like kind of each and every positive definite matrix will work for.
It is positive that if gamma k is bigger than zero. If gamma k is positive, then diagonal matrix with such values, main diagonal is.
Instead of using diagonal matrix, can we use any arbitrary positive definite matrix? It will work.
Yeah. Many people ask questions during my presentations. Why to use another parameter? Is it necessary? If you multiply tk and tk, then we will obtain no parameter. Because the numerical experience confirmed that it is true and better results. Finally, can we drive car 120 kilometers in first day? How must be second, third, and theta k is this to change speed. Change.
What is the full form of SN?
SM Stanimirovich, my surname, Miladinovich, another. SM.
Any other questions? If no question, let's get it. It's fine. Question?
Theta, maybe theta S.
No tea time now.
Depend on.
I'll talk about basics.
Yes, we need basic, but
Pointed.
Adjustments.
Pointer is here. Back. Back. Yes. Start. Yes. Okay. So thank you very much. So we shall start now some basics, whatever Professor Pretark used some high-fi term like some decompositions. So we'll learn some basic sensitivity analysis of this matrix decompositions. So first of all, we'll learn how many types of decompositions. There are many matrix decompositions out there. And one of the most important decomposition is any decomposition. And that is called Gaussian elimination. So in this LE decomposition, there are many things we should learn that many of you don't know what is their sensitivity and when we can use, when we cannot use. So all these things we will learn from my lectures, some basic lectures. Okay. So some of these overviews are there. We'll be covering entire this session in 10 days. Matrix decompositions, basically LE decompositions and Cholesky factorizations. And we have to read some forward substitutions and backward substitutions. And how many flops required to compute this by forward and backward substitutions. Okay. And also we'll learn some other things like matrix norms, some details, and their sensitivity analysis like condition number and the perturbation theory of these methods. Okay. So first of all, I would like to give you some motivations where we are going to use the matrix decomposition. Say for example, if you have some differential equations, say boundary value problems, and equation of this like this, and this boundary values are like this, and you can when you discretize into the grid leading to a system of linear equations. So in that case, we can use LE decomposition, which decomposes a matrix into product of lower triangular matrix and an upper triangular matrix, and then we can solve the system of equations. Okay, so these are things. Now, similarly, you just take this. If you do this by the discretizing in the interval 0 and L, where n plus 1 evenly spaced points, where xi equal to IH, and the step length is of this form. And then you have this difference skip you can use this one, and after this you will be getting some tridiagonal matches. Okay. So if you have difference approximation can be written as this like this, y equal to n f equal to this, and finally we are getting the systems of equations. And this system, this matrix equation is nothing but it is a tridiagonal, because why it is tridiagonal? It has only the super diagonal, these are the super diagonal, and these are the main diagonal, and this is the subdiagonal. Okay, and that's why it is called tridiagonal matrix. Okay, and this solving this kind of equation sometimes it is difficult when the matrices are in condition. I speak about what is the in condition matrix and well conditioned matrix, all the details. Okay. So like another boundary, another say differential equations, if it is of this form, and there are a lot of this physical interpretation by ux and u double dash x diffusion, convection, and decay, and then similarly we can use this interval and the step length is of this point, of this form, and then the grid points are like this, and then finally you use the difference approximation and with this numerical scheme, and finally you will be getting the equation of this form, and where usually m equal to 0, then au equal to f, and when m equal to 6 and step length is equal to 1 by 6, then you can get the equation, matrix equation of this form. Now the question is, if the matrix of size is more than 6, say for example, 10,000 by 10,000 matrix equation, if it is there, for solving such equation is difficult. Okay. So this tridiagonal matrix system can be solved numerically for an approximate solution to the boundary problem. So now the question is, if you have differential equation and when you discretize and you give the differential skill, finally you will be getting the matrix equation. And this matrix equation sometimes it depends on the problem. Okay, it can be the bigger size and it can be smaller size. You know. So if the problem is bigger, say for example, in the matrix size with 10 million and 10 million matrix, so how you solve this equation? For a small matrix equation, it is quite easy. You can solve this. But if it is a big matrix equation and the size of the matrix is big, then it's difficult to solve that equation. In that case, we use the LED. Okay. So now the question is why you are using LED. So for example, AX equal to B equation is that A is a non-singular matrix. Then in your MATLAB you can put X equal to A inverse B. You know. But in generally, numerical linear algebra to avoid computing determinants because inverse contains the determinant. So join and put factors are there. If the entries of the matrices are very near to 0, in determinant you are computing, you are multiplying, you are adding, you are subtracting, you are doing lot of things. Okay? If these numbers are very close to 0 and it will be again going to 0 and your computer will be this. In that case, you won't get the correct result. Okay, and sometimes you will get a very big result which is beyond from your exact solution. Okay, and sometimes you are getting not at all solution. Okay, so in general we avoid calculating the inverse. So there is alternative method is what was iterative method. Okay, and one of the iterative method is LED. Okay, and we will see that this calculating inverse as usual method by determinant and the vectors, and we'll get the floating point operations will be much bigger than by going through the iterative method by any decomposition, which will be this. Okay, in that context also we are avoiding calculating the determinant matrix. Okay. Now this inverse. These are the basic results, you know. Inverse means you can write all these five properties of this inverse. Either you can say the A inverse exists, or there is a non-zero vector Y such that AY equal to 0. And the columns of A are linearly independent. Similarly, rows of A are linearly independent, or you can say determinant of A not equal to 0, and in the 50th and 60th also independent. So these are the all are equivalent condition for the inverse of matrix. Okay. Now, in this iterative method, basically we are using three operations, three elementary operations, three fundamental operations. Those operations are, you know, the elementary operations. We tell that swapping two rows or two columns. Okay. Useful when a pivot is 0 or small. Generally, when your the pivot elements will be near to 0. In that case, you are replacing, you are interchanging two rows with this. And these are very important. And row multiplication. What you do, you just multiply one row by some non-zero scalars. Okay. In that case, also such scales the equation doesn't change the solution. Okay. If you do scale, and your solution will get changed. This is the beauty of elementary operations. Okay. And this row additions. Also, you can sometimes replace this row by Ra plus K Rk. So these are the fundamental rules we are using in the linear algebra. You know, all this matrix decomposition, any decomposition, even QR decomposition, so all these three operations we are using. If you do multiply or do swapping the two rows and multiply one row by A and interchanging adding, and your solution will get, say for example, AX equal to B. And after these three operations, you are getting some another matrix equation, say Lx equal to B, and the solution of Ax equal to B and Lx equal to B is same. And this is the beauty. So all these three elementary operations will be beauty, and we'll see how things are laying out. So key idea is these operations preserve the solution and set the system and are the basis of the method like Gaussian elimination and LED decomposition, as I told before. Okay, so LED decomposition, what it says that LED decomposition of a square matrix A is expressed as A equal to A. L is a lower triangular matrix and U is the upper triangular matrix. And sometimes it is in LED decomposition it is coming unit lower triangular matrix. The diagonals are 1, 1, 1, where L is a lower triangle and these are matrices. Okay. Now you see how we are solving this. Given Ax equal to B, and you just replace by A by LU, and you solving LUx equal to B. Just you take Ux equal to some G and Lg equal to B. Yes? So what do you do? Generally, if Ly equal to B, and if L is the entry, say L11, and all these entries are of lower triangular matrix, Li's are the entries of the lower triangular matrix, and these are the solution you can get. If it is a lower triangular matrix, you can go from forward substitution. Okay, first you get the y1, and then you can y2, and if you know y1 and y2, you can get y3, and so on. You can get y1 finally. Okay, so similarly, you are using ux equal to y using backward substitution, and then ux equal to y. So first you get the xn from the back side, and you are coming to the xn minus 1. Once you know xn minus 1 xn, you can get xn minus 2. And once you xn minus 2 you know, then you can find xn minus 3, and so on. You can find xn. Okay. So these are the process to use the iterative method instead of using the determinant method to find the inverse of the matrix. And from here we can see how much floating point operations we will be getting. Okay. Now here, how to use your MATLAB to solve these equations. Say for example, if it is a 2 by 2 and 3 by 3 equations, you can solve through your hand calculation. But if it is a million by million matrix, you can just write your one small program in MATLAB, and you can find the solution. Say for example, if you have a lower triangular matrix, and you initialize the vector y, and for I equal to 1 to n, and you just take the loop of this one. And this Lii is not equal to 0 because initially we have included A is a non-singular matrix. If A is a non-singular matrix, then L and U should be non-singular matrices. Otherwise, it is singular. Because determinant of A equal to determinant of L into determinant of L. So any of this, L and U, there should be non-U. All of these at a time should be non-U. Okay. Otherwise, a matrix would be singular. So here L is a non-singular matrix and U is also a non-singular matrix. So you can get this, and finally you can get the output of this one. The complexity, that means floating point operations. Say when you put in your computer, in your MATLAB or in C programming, so every computation needs time. Sometimes it is called a complexity, and sometimes we used to tell in numerical linear algebra floating point operations. What it calculates? Each operation, either it is addition or subtraction, or it is multiplication, or it is division, or it is exponential. Each one takes one block. Say addition, one block, multiplication, one block, calculating all at a time, and finally we will be getting all of these. How it is using the VI, this is one, this subtraction is there, and here is multiplication is there. So in one operation, we use 2 blocks. You know, 2 blocks, and you take I varies from 1 to n. Yes, sir. And j varies from 1 to I minus 1. If you add all total, and you will get n square plus some n terms in terms of n. So when n is very large, as compared to n, it will be n is very less. So we keep by the order of n square. Right? So these are coming from here itself. Just you do This is called LU decomposition. This is equation Ly equal to B, and this is forward elimination, and you are going towards forward. Yeah, question.
In I running from 1 to n,
Yeah.
if you consider I is equal to 1, then in that case, j running from 1 to 0.
Huh?
I running from
Because this is the upper triangular matrix, okay? This is our upper part, lower part of this, this is lower triangular matrix, okay? The upper part of this will be 0. So that's why beyond I, upper part will be 0. So lower part only we are giving, so the loop will go from A build from one part to B. Because upper part is not there, okay? All are 0. So we are not taking into account. Even if you are counting unnecessarily, you are giving the load to the computer. So we are able. If you take like this and the floating point operation is unnecessary, okay? If you know these components are 0 and their corresponding solution would be 0, then you no need to put this, okay? So similarly, we are going for this backward elimination, and the way we did for the forward elimination, and you can go for the backward elimination, and you are doing I varies from n to 1, because as we have seen, first we got xn, then xn minus 1, and then xn minus 2, and so on, xn. That's all. Okay. So likewise, it is I varies from n to n. First you take n minus 1, and n, and then finally you take this loop. With this we are getting from our previous slide, and then you just n for loop. Just you write 3 lines, 4 lines in MATLAB, and you get the solution of this, and get the solution of this. And the complexity is other. Okay, and just you take this summation to j varies from I plus 1 to n, and here I varies from 1 to n. Okay, and if you do add, you will get n square plus some other terms, n and some constant will be coming. You just ignore because n is very large. Okay. So likewise, when you solve this matrix equation A equal to NU, you need forward, backward substitution, and then also you have to calculate NU. So for calculating NU, you need some plots. Already you got for the forward and the backward substitution, for example, n square plots and 2 n square plots. Now we need to see how much plots we require to compute the NU. Okay, if you do total at the time, then you can find out how much plots you require to solve the equation Ax equal to this. Understood? So likewise, we just see how the decomposition is useful, whether this any decomposition is useful or not in your block. Okay. So here the block comes LU. The LU decomposition says generally we are taking n by n matrix, and we are taking non-singular matrix, because if you take non-singular matrix, then LU decomposition will be unique. Otherwise, LU decomposition for a singular matrix you may find, but it is not unique. So there are n minus I operations are there. So because basically I'll tell you later part of this slides that how we get this much flops and this complexity is order of n cube. I'll tell you later part of this one. But we need order of n cube flops for calculating LU. So n cube, and previously we got order of n square. So n cube plus n square. Again, you can say you can very large, you can ignore n square. This total flops requiring order of n cube plus 1, the system will be. Okay. Okay. So as I told you that the forward substitution. So first you got this. This is the 1 flops 1 and 2 and 3 and so on. You will be getting this, and finally you will be getting, if you add this and order of n square you will get. And similarly for the backward substitutions, the calculation you can find, because first you need 1 division, and then second and the third, and the number of steps will increase as I varies from 1 to n, j varies from I to 1 to I minus 2. Okay, the first step 1 plus, 2 plus, 3 plus, and so on. N minus 1 plus, because n minus 1 addition, and you can just by looking and the calculation you can find, and finally getting order of n square. Okay. So now, as I told you, just you got this n cube flops for this for getting LED decomposition, n square and n square, and total n cube flops very large. Okay. This makes LED decomposition is an efficient method for solving system of equation, especially when solving multiple system with the same coefficient matrix A but different right-hand side speed. Okay. And this LED decomposition is a powerful and this efficient method for solving the system of linear equations. This is efficient, and later on I will show you that in some application this won't be useful. Okay, when the problem is the real condition. Okay, now what is real condition? I will tell you that. Just to see this how it is. This LED decomposition of n by n matrix order of n cube flops, while forward and the backward substitutions require this n square flops. Okay. And LED decomposition is particularly useful when solving multiple systems with the same coefficient matrix, as it avoids recompleting the decomposition each time. Here is a Gaussian elimination. Works well for many systems of linear equation. It can be numerically unstable. And just in previous slide, I told you that this will be very useful for solving the system of equation. And in this slide, I am telling here, it can be numerically unstable, and especially when the matrix is infinite. Okay. So unstable means if we have a system of equation Ax equal to b, okay, and you are expecting some solution, but you are getting it far away from your expected solution. In that case, we tell this is unstable. That might say, for example, you are giving system of equation to solving the MATLAB, okay, and then you know that the solution would be like this, okay, it would be nearly one. But your computer gives the result which is very far from your exact solution. In that case, that instability will become. Okay. And especially when the matrix is in condition. So in condition means like this, when the system is there, and if you do a small change to that matrix, small change, and its solution will get large change. That might be. Say if you are giving a one component of the matrix, one entity of the matrix, you are changing a little bit, say, for example, it is 10 to the power minus 3, one entity. And the solution is going from half beyond from 10 to the power minus 3. In that case, that matrix is called in condition. Okay. The variant of Gaussian elimination, such as partial pivoting and the complete pivoting, improve the stability of the algorithm. In that case, what we are doing, if the Gaussian elimination without pivoting, it won't work, and it will be difficult for you to calculate the real conditioning problem. In that case, you will be using the partial pivoting and the full pivoting. You know already that. What you do, you just search in the column, and the one is bigger one, you just switch it off to top one to make these pivot elements. Okay. So once you did, then you do the operations, elementary operations. Okay. And similarly, in each step, you would be the partial pivoting. Okay. And still, you will find sometimes that there are many applications where partial pivoting won't work. That means that problem is in conditioning. If it is in conditioning, then you are going for. In that case, what you do? You search the entire rows and the column, the bigger one, bigger entry, and you use the elementary operation. You take as a pivot element to the top one, and then again you do the elimination process and make it a decomposition. But the problem is the full pivoting, the decomposition is stable one, but it is very expensive. So that's why people don't use this partial full pivoting. Okay, but partial pivoting it is useful, but it gives sometimes longer results. Okay, as I told you, the partial pivoting is a technique used to avoid the dividing by small numbers. Okay, which can lead to numerical instability. Second, in partial pivoting, at each step of the elimination process, the pivot element, the element used to eliminate entities below it, and is chosen to be the largest element in the current column. So once the first operation you have made, in the second operation, again you have to do same way, you just search the biggest one and you take this out. Okay, by using the elementary operation. And sometimes you will be using the elementary matrix instead of elementary operations, because elementary matrix you will be coming from elementary operations. Okay. So this is done by swapping the rows so that the largest element is moved to the pivot position, as I told you. Okay. The steps for the Gaussian elimination of the partial pivoting are: at each step of the forward elimination, find the largest element in the current column among the rows that have not been eliminated. Swap the rows, as I told you, and the partial pivoting helps to reduce the risk of dividing by small values, thereby improving the numerical stability. Okay, so in this way you can improve your numerical stability. Okay. And now the complete pivoting is here. The complete pivoting is a more advanced technique that not only swaps rows but also swaps the column. When you have to search the entire rows and column, you just see the largest element of that. At each step, the largest element in the remaining submatrix is selected as the pivot. The rows and the column containing this element are swapped. Okay. So the complete pivoting, this one, that provides the even better numerical stability than the partial pivoting, as I mentioned before, but it is computationally more expensive due to additional column swapping at each step. Okay, so this is the way we avoid the swapping, unless and until you know the drawbacks of some decomposition. If you are going to use in your calculation, sometimes it is dangerous. So one is to know the type of this. The advantage or disadvantage. Now we have to know what is the advantage and disadvantage. Both the partial and the complete pivoting improve the stability of Gaussian elimination, but they come with the trade-off. But the partial pivoting is easier to implement and computationally more efficient than the complete pivoting. It is typically sufficient for most applications and is widely used. So people are using this. Okay. And the complete pivoting that provides a better stability, as I told you, and especially for very ill-conditioned matrices and matrices, but it is more computationally expensive. I'll tell you about the ill-conditioning more details. I think later slide to know more. Okay. This part, the conclusion of Gaussian elimination is a fundamental algorithm for solving the system of linear equations. And its variant such as partial and complete pivoting enhance the algorithm numerical stability, especially for, as I mentioned, the choice of pivoting strategy depends on the specific problem being solved and the computationally researched. Sometimes you will find there are applications where you can use successfully this linear decomposition because there will be no problem. So for example, your matrix in well dimension. In that case, there is no problem. Okay, and people are using it. It is not like that always it is always it is a problem. The people are using to solve their day-to-day problem by using it. But computational point of view, there are applications. There are matrices. There are in various applications in data science, machine learning, and there are many complex problems, NP hard problems. In such cases, all are dealt with elimination. Okay, in such situations, in such problems, one needs to be careful while using the LED operation. Okay, and now the basic Gaussian elimination. Basic Gaussian elimination method is efficient and widely used, but in practice, pivoting techniques are often necessary to ensure that solution remains accurate in the presence of round of error and inconsistency. Okay, second decomposition I am going to tell you. I'll come back that how much blocks you require for the LED decomposition. Let's start this LED decomposition. This Cholesky decomposition is the matrix equality definite. In that case, you can write in this form A equal to LLD. where L is a lower triangular matrix, and sometimes you can tell that L is the upper triangular matrix RRT, because if L is lower, L transpose is upper. So one some book, I have also written the letter for RRT, that means upper triangular matrix. And here what we need this only, you need this lower triangular matrix, and you just Ax equal to B, and you do substitutes Ly equal to B and Ltx equal to Y, where Ly equal to B, because Ax equal to B, and you do substitute Ltx equal to B, and you put Ltx equal to Y, and then you solve Ly equal to B. And same way as I discussed in the previous slides, by forward and the backward substitution, you can get this, and you can also get the order of n square plus. Okay. Now, Cholesky decomposition is computationally efficient for positive definite matrices. As I know that positive definite matrices, this is a very good matrix, okay, and it is symmetric, and it is a quadratic one, which is strictly greater than 0, then you can apply this, and its application significantly reduces the number of operations compared to the other factorization methods such as LED. In general, in LED decomposition, we need 2n³ by 3 flops, 2n³ by 3 flops. And in Cholesky decomposition, we need n³ by 3 flops. Okay. So Cholesky factorization, we need n³ by 3 flops. So for Cholesky, LU, we need 2n³ by 3 flops. And for Cholesky, LT, you need n³ by 3 flops. And here matrix A is non-similar, is not equal to 0, and here you are taking the symmetric and positive definite. XTAX. These two conditions you need. Okay. These two conditions you need, and in that case you will be getting the Cholesky factorization. If you know the matrix is positive definite, instead of using any decomposition, you use Cholesky factorization. In that case, you have taken the half of this n³ by 3, not n³ by 2. This is n³ by 3. N³ by 3 blocks you require that for the calculation of this one. So basically, we are using this. If you do take this right hand side and the left hand side, and you just take the ith term of A and the ith term of the right hand side, if you do equate, and the diagonal terms would be looking like this. Okay. And the non-diagonal terms, when I greater than j, because this is lower triangular matrix, the upper part is 0, so we don't need to calculate the upper part. That's why we have taken I greater than j, because all the other terms are the 0. Okay. And here you can see that k varies from 1 to I minus 1, and here is k varies from 1 to j minus 1, and j is yes. Here is j equal to ik is there. So you will getting the Cholesky factorization. Also, it is order of n³ for operation to compute, which is more efficient than LU decomposition for solving the system with the symmetric positive definite matrices. Okay. So basically, it is n³ by 3. So due to if n is very large, as compared to n 1 by 3, nothing. That's why more than we are taking. And if you do compare, you just see here 2n³ by 3 blocks, and then we taking n³ by 3 blocks. That means half of this. And if your problem is say 10 by 10, you should do calculate this way. And also you get the other terms, n terms and the constant terms. So if it is a small matrix, it should be that. Say if it is a very big matrix, million by million, 10,000 by 10,000 matrix, in that case, our n³ plus 3 to take this one. Okay. So same way we are solving this to the Cholesky factorization, and you are finding, and finally you will be getting this n³ by 3 blocks. And it's a calculation. I can show you that this forward substitution, backward substitution, same way you just proceed as we did for the LU decomposition. The order of n² flops for the backward and the forward. So 2n² means this is order of n² flops, and so on. You are getting n cube plots for the Cholesky factorization. Okay. Okay. The computationally efficiency, how this Cholesky decomposition is computationally efficient for solving the systems of linear equation, particularly for the large matrices. Because this positive definite matrix sometimes it is a well-conditioned matrix, but it is not always true. There are examples which are symmetric matrices and positive matrix. They are in condition. I will tell you later part of this. It's called Hilbert matrix. That is symmetric and it is positive definite matrix, but it is unit. Okay. If it is not in condition, in that case, the Cholesky will give you the correct answers. Okay. Okay. Cholesky decomposition is, as I told you, unlike the LU decomposition, Cholesky decomposition doesn't require pivoting, which reduces the potential for the numerical instability. Additionally, since the matrix A is assumed to be positive definite, it ensures that the matrix L will contain only positive values on the diagonal, avoiding the possibility division by small numbers. So if it is a positive definite matrix, obviously its diagonals are non-zero positive, and you know that eigenvalues are strictly positive, greater than zero for the case of positive definite matrix. However, if the matrix is not positive definite, near singular numerical errors can arise and the decomposition may fail to produce the valid result. So here, main idea is we are not going to just decompositions because you know the decomposition. What is the decomposition? But here, more important is we need to know how it affects with our calculation. Whether it is our research. Should we use this method or not? So we can decide by all this instability, floating point operations, whether it is ill condition or not. Because many people they are experiment doing all are getting matrix equation. Data scientists also getting matrix equation. The physics people doing in the lab they are also getting matrix equation. And the vibration with the mechanical engineer also they are getting matrix equation. Even this differential equation they are all getting when you do discretize and you get the matrix equation. Everywhere, every and scientists using the matrix equation. More or less. At the end of their calculation, they have to find their matrix equation, they have to solve everything. How accurately you are solving your equation? Important part of this session. Okay. From this LE decomposition, we can find the another decomposition is called LDB, where L is unit lower triangular matrix and D is diagonal matrix and D is unit upper triangular matrix. So A equal to LD. If you get this and L is unit, L and you can write LDB, where you just extract U equal to DB and just you take D equal to diagonal of U11 and so on UN. Okay, and B is this is 11 and this is upper triangular, okay, and this is B. So just you are extracting the diagonals of B, the diagonals of B, okay, and this if it is this you can just write in the terms of LDV, where L is a unit lower triangular, that means the diagonals are 1, 1, 1. And D is a diagonal matrix, and which diagonals are the diagonals of the U matrix, and V is a unit upper triangular matrix, and where this one, L is unit lower triangular matrix. So now with this, the proof is a small thing, you just write down L and D equal to diagonal of this, and just you put this U equal to DV and B equal to D inverse U, because D will exist because this is a non-singular matrix, the diagonals are non-zero, so D inverse exists, and then you can find A equal to LDB. And this uniqueness you can find in this way, and finally you will get this matrix equation A equal to LDB is the unit D. You can write. Okay. So similarly, if the matrix is symmetric, and then you can write A equal to LD, LT. This L is a unit lower triangular, D is diagonal, L is unit upper triangular, L transpose is unit upper triangular matrix. So from LU, you have LDV, and if there is a symmetric, then you have LD validation. If it is symmetric, then RT is safe, then you can find this equation. So from LDB, it's just the idea is this: A equal to AT and LDBT, and here you can write this. This is also an LDB decomposition, and this uniqueness implies B equal to L transpose. So this is a quick proof of these equations, because A equal to A transpose. So for example, if you have a matrix equation A, and then you can apply this LD decomposition and do the row operations and get this updated matrix. Okay, so pivot element A2 is -1, and use this, and this row you are taking this because you know all this, and then finally you can see this. This is unit lower triangular because diagonals are 1, and this is upper triangular matrix. So we got the unity combination. And if I extract the diagonal and with a D matrix, and then it will be 1, 1, 1, and so I can write immediately. Okay. Clear? So similarly, we can use these are basically X equal to B using the Gaussian elimination. A can be reduced to upper triangular matrix for using only type 1 row operations. Okay. So what you are doing basically when Gaussian elimination, basically you are doing this. You are taking the pivot elements, okay, and you are dividing this. If this pivot element is a whole number, or it is a bigger number, and you are just keeping, and if it is very small, it is near to 0, then there will be the problem. And when A11 is very near to 0, then you can say that matrix sometimes is infinite. Okay, that means you cannot accept the good solution. Okay, so in that case, what you do? You use the partial priority. You just go throughout the column and you take graph the one, make a little bigger, and you keep this at the top, and by using elementary operations. So once you do this, you can and you are doing the operations. So rho I equal to rho I minus mi1. This is the multipliers. These are the multipliers and 1. So first row you are getting this calculation. Okay. And this calculation, the first operation, you need n square plus. Because every time you will see that this one multiplication is that, and this is one subtraction is that. So each step you take the 2 flops and you just I varies from 1 to n, and the row itself contains n minus 1 number, and the row I, row 1, and this contains the n minus 1 number. So you do multiply and you just see, because n is 1 and this is 2, and each time you are taking multiplying the n entries, n minus 1 entries. So all these calculations needs to get this in the step box. Okay. And in the second operation, so what you just destruct this first row and the first column, and you will be getting this sub matrix with n minus 1 by n minus 1. And again you just perform the same way. And in the second part, you will get n minus 1 whole square, because the sign is 1 less. And in the second time, your size is 1 less. Okay. The first time it was size is minus 1, n by n. It takes a n square plus. In the second part, you just take the n minus 1 whole square with the size of the matrix is n minus 1, and you are perfect in the same way. So likewise, if you do substitute this n minus 1, this is every time division is coming in that calculation. You remember dividing by the diagonal elements. And these are like n minus 1 division. Okay, each time you are dividing. So n minus 1 division you have, n minus 1 square multiplication is there. So total plots for one case is this one. So finally, you will be getting the upper triangular matrix like this. Okay. So the performance, as you have seen, the triangular form and the back substitutions, and we are getting this is the calculation. The for k equal to 1, and you are getting n minus 1 whole square, and so on. Because why it is n minus? Because first entry you are not touching, and then you will be getting 2n2 by 3 plus. Okay. So Gaussian elimination without pivoting cost, this is 2n cube by 3, as I told you, and if n is very large, so 2 by 3 is very small as compared to that. So that's going into a little in flux. Okay. Time?
8 minutes.
8 minutes.
7 minutes.
Okay.
10 minutes. 10 minutes.
Okay. So here the performance is like this, that to compute the y and to compute the x, 2n square plus, as I told you the before. And the finally, when you solve Ly equal to b with the multipliers, see generally we are getting the multipliers. Okay, this mi1. If you write that equation, that is nothing but the lower triangular matrix with the diagonals are 1 1 and the below the diagonals all the multipliers. And that multipliers would take the shape like this, y1 equal to b1, and if you do right, and you will get the matrix equation of this for this L equal to L of this matrix, L equal to like this 1, this n2 1, and this n1, this 1, and like here you will get n2 and so on. These are the multipliers you will be getting when you use the Gaussian equations. So basically, you will get the L and U, Ly you will be getting. L is a lower triangular, row oriented. This. Now, similar things we can do by using the elementary equations. Whatever we are doing the elementary equations, or say, for example, if we want to use this elementary operation, say. If you want to interchange 2 rows and the 2 columns, so instead of doing the operations, I can use this A11, A12, A21, A22. Say, if it is this, I can use say 0, 1, 1. So this is my elementary matrix. And if you do that, you will get A21, A22, A11, A1. So this is what this is elementary operation. And it interchanges in 2 rows. Instead of doing this, so if it is a big matrix, if it is a billion by billion matrix, you need to go this row 1 is represented by this, row 2 is at a time you just the elementary matrix will work. Okay. And similarly, if I want to multiply one row with this one, so I can write this one m0. So I need this a11, a12, say a21, a22. So I can just get this a11, this one a11, this a11 plus a12, or this is 1 and then flip of you take this here 1 m and 0. So if they do multiply, you get some multiple of m. So likewise, so any matrix you can multiply with the m is the multipliers, and this is 1 I plus mij. This is identity matrix of same side n by n, and this the multiplier, and eij. This eij means in the ith place ij plus 1, and the rest of the entity of the matrix will be 0, and you will get the elementary matrix. The elementary matrix is a determinant is always equal to 1. And determinant of A tilde and determinant of A will be same. So if you are multiplying with the elementary matrix, it's a determinant won't get changed. And also it will be easier to calculate the inverse of the matrix. So for example, you are finding the inverse of the elementary matrix, just you are looking the off diagonal everything will be opposite side. So if it is a positive, you make it negative. So no need to calculate, no need to use the elementary iterative method to get the inverse of that matrix. Also no need to calculate the determinant and the coefficients. So likewise, the elementary matrix is non-singular always, and it is very good to calculate the inverse of the matrix, and it would be very friendly, so you can use that way. So these are coming from elementary operations. Okay. So here determinant is, and this as I told you that EM inverse, you just take the negative sign. It is a positive sign, you just take the negative sign of diagonal. This is also type 1 operation, elementary operation of type 1. That is multiplication of this. Okay. So here, as you interchange the two words, so if you do multiply this determinant and this determinant would be of that change of sign. Because if you are interchanging two rows, determinant would be negative. And if you two times you are doing, then it will be multiplication. Okay. So elementary operation is the main job and to make it simpler to calculate. So like with all this, if A is symmetric matrix and row operations, if you are doing this, then if it is a symmetric matrix, then you can say that A tilde transpose equal to A tilde is this one. And symmetry is pretty that. If it is symmetry, and if you do multiply with the elementary matrix, also it will be. Okay. So flop counts for the Cholesky decomposition, as I told you, if you take the left hand side and the right hand side, because A equal to say RRT or LLT UPR, because A is known matrix. You need to convert either RRT or LLT. Is not good. So just equate ideal entry from the left hand side to the ideal entry to the right hand side. And if you do this, then you will get immediately R11 equal to square root of A1. And since this can be the plot of mind, because A is the quadrilateral matrix, your diagonal ability should be positive. So we will not negative. So I am getting the point. Okay. So likewise, you will be getting the entire column of this A1 they will divide into provide Rn and the completes the first row of the R and the first column of R. Similarly, you can just calculate this Rii, this is diagonal elements, and this one is this, and J less than 1. And finally, these are the loops. C k varies from 1 to I minus 1, and k, this is I minus 1, and j varies from I plus 1 to n. So all you will take each time you are taking two flops, because this is one multiplication, one subtraction. So each time you have two flops, and the loop is running k from I to I minus 1, and j varies from I plus 1 to n, and I is again running from I 1 to n. So three loops in this will be one. From this calculation, K half J varies from I plus 1 to n, K varies from I 1 to n, and I varies from 1 to n. So finally, you have this calculation that if you have, you can just calculate this R12 and R1 like this. And finally, you will be getting your upper triangular. As I told you, that the loop has each time you are doing two operations, one is addition and one is multiplication. And the square root is also there. So if you square root is under one class. Okay. So first you have to calculate the multiplication addition. And then you can look for the software square root and division. So square root is straight division, and hidden is the straight division for I will do 1 because each time 1 million, each time 1 million. So you can block. And the square root is 2n plus. You have. But here you these two plots you need to look. And as I told you, J varies from k plus 1 to I varies from k plus 1 to 1 and k. And you just do the arithmetics, and finally you will be getting this calculation, and then you will be getting it by 3 plus. So just you write the additive method, if you know, and from there you can know the complexity of the equation. So finally you can decide which method, which decomposition will be helpful to you to your problem, and whether plots need more or less. Even if the plots are more, and if your algorithm is stable, you prefer that. Now the one which the plot is less, but it is in condition, and your method is unstable, your algorithm is unstable, you just avoid and you just go for the higher plot ones instead of lower plot due to the stability. So similarly, you have this other n cubed by 3 flops, as I told your Cholesky factorization. And say, for example, as I told you to calculate the A inverse. And if you do A inverse, how much flops you require? And the A inverse by determinant adjoint cofactors, how much flops you require? And the inverse by using the identity method. How you use the identity method? You just see this. Generally, what you do is we say X is the inverse of that matrix, saying that when the Ax equal to I or X equal to I, generally you do. And what here is I just divided into n columns of this equation, and I equal to this is E1, E2, En. That E1 means the first entry is 1 on the x star 0. That means En higher entry is 1 on the x star 0. And then you forming the x I equal to E. It is exactly what you did in the previous, the x equal to. Okay, and this x I equal to Ei, and Ei having 1 in the higher entry and the rest entry are 0, and then you calculate the LU decomposition of each one, and the A equal to LU of each one. So each one takes how much block? 2 N2 by 3. Okay, and how many N has? Then x I get it to 1 block. But each I you are getting 2 N2 by 3 block. You know, if you are getting everything. So you have N size. So N4. You know, because each one I x I equal to E I. X I is a vector, A is a matrix, E I is a vector. So if you use the LU decomposition takes to solve the x I equal to E I for 1 I is 2 N2 by 3. You have this N4. So A inverse takes N4 to block. Okay. Yes, by using 2 N2 by 3 by using this. And if you use determinant of effect, it will be 8 N2. So if you go by this 8 N2 by 3, it will take like this here, 8 N2 by 3 block, and then finally you will be getting the x equal to be the solution of this. Now, if you have time, we can continue, otherwise in this. How much time?
It's already one.
Already over. We'll stop here. We'll discuss. So more generally, I need to say is that the cost of slightly less. This is 8 N by 3, and if you solve it by using the A inverse technique, by using the LU, and same thing if you do complete the determinant, it will be huge. So try to avoid this determinant protector. We are doing this. In the computational aspects of these things. So in the same way, you can save your time. Okay, thank you so much. If any question, please. Any question?
I want to say something with the best intentions, how to say it. First, my comment, something to add to your talk is that we use the L transpose decomposition computing G inverses. Because L transpose decomposition can give some kind of full rank decomposition, and we then can compute more velocity.
Yes.
Another generalized inverses.
Yes, but here we are talking about the non-singular matrix. That's why it has a full name. And also
In case of singular matrices, we
yes.
have some trapezoidal
Yes.
matrix, will not be triangular, trapezoidal.
Mm.
And finally, we wanted to work this in symbolic form. But when we used L transpose decomposition, we obtained square root. Sometimes square root appears. It was in your formula 1 for 13, I think. Square root is there. But if we used L transpose decomposition, we will avoid square root.
Yes, but the LDB is square root is not one. LDB.
And it is much easier for symbolic computation to avoid square root. We can work on polynomial, on algorithms with polynomials.
Yes.
Rational functions.
Yeah.
And only to mention, if we swap to two rows, columns, multiply, and add, then it should imply some permutation matrices left and right.
Okay, yeah.
In this way, LU factorization will be PA equals LU factorization.
Yes, so this is for partial binding. Yeah, three permutation matrix. Similarly, if you can do it from the right, that means the permutation of the column mass. The mass will go and like this, if I do multiply 0, 1 and 1, 0, the row interchange, that means same thing if you do multiply on the right, it will be column interchange. So this is the partial value.
Yes, because each transformation of rows commons is equivalent to multiplication with an appropriate permutation matrix. We multiply such permutation matrices and finally we obtain that final permutation matrix from left and another from right.
Yeah.
It is not necessary to trace each with some commons and so on. Yeah, sorry.
Thank you.
Best intention.
So, we have no question, we'll stop here.
So we'll have tea break or?
Yes, we have.
Whatever it is, slide up on email, right?
When will we continue? What time?
After this tea break,
After the break. Okay.
5 o'clock, I think.
After the break.
Next miracle is